Hello, everybody. Welcome to the first spring colloquium for the physics department in 2026, also the first one in 2026. We are lucky to be joined today by Professor Leo Stein. He's currently an associate professor in University of Mississippi. As you guys will shortly find out, his specialty is black holes, the gravitational waves that come from them, and what astrophysical observations in general can tell us about the nature of gravity. And he received his BS from Caltech and then PhD from MIT. Then he did a NASA Einstein Fellowship at Cornell. And then he was also a postdoc at Caltech before he started at Mississippi. Since then, he's been a recipient of an NSF Career Award, a Sloan Research Fellowship, and he's been a Kavli Fellow at the National Academy of Sciences. He is also currently the Secretary Treasury of the DGrav for the APS, although as he will remind you, that ends in 2 months. So if you want him to do something for that, you better ask quick. And he is also on the Simulating Extreme Spacetimes Collaboration Executive Committee. So we're very lucky to have Leo here today to tell us about the subtleties of the relativistic two-body problem, both its numerical and analytic sides. All right, Leo, I think you can turn your microphone on and take it away.
Thanks, Cindy, for the great introduction and for the invitation to come visit and give this talk. Does anybody know the name of this pixelated painting that I put up here? Persistence of memory. Very good. All right, so I'll talk about gravitational memory later and how you can see that it is not resolved on the right and it is better resolved on the left. Okay, so is my clicker working? Let's try that again. Yeah, clicker is working. All right. Let me give you a little bit of motivation about why we care about simulating black holes and the gravitational waves that they produce. And then we'll talk about a little word from our sponsor, advertisement for the latest catalog of numerical relativity simulations from the Simulating Extreme Spacetimes collaboration that I'm a member of. And then I'll hopefully get to talking about the subtleties of the binary problem in GR and how analytics and numerics talk to each other. All right, so motivation, why? Interesting. Oh, okay. Why do we care about simulating black hole mergers? Well, I care about it because now we can actually detect these things with real detectors like LIGO and Virga and Kagra, which have most recently finished the 4th observing run, and we now have, I can actually say, hundreds of gravitational wave signals that have been detected, and we're actually learning things about the universe from binary black hole mergers being detected by real detectors instead of just theory. All right, so if you don't know how these things work, it's a very fancy, oh, that's supposed to make a movie. Yeah, it's a fancy Michelson interferometer, which we all learn about when we learn about special relativity. So the thing that proved that there is no ether now is used to measure gravitational waves. It's of course much more complicated than that simple picture showed. There's actually super complex optical train and control system, and many hundreds of experimentalists work to make these, some of the most sensitive instruments that have ever been built. And of course, there are detectors that haven't been built yet that are planned for the future, which will be even more sensitive. So this is a kind of cartoon of one of the future detectors called the Einstein telescope, or maybe Cosmic Explorer. I don't remember which is which. But this is supposed to be underground in a triangle configuration instead of an L shape. And there's also, now this is actually funded. There's a future space-based satellite mission called LISA, that's the Laser Interferometer Space Antenna, which will work at much lower frequencies and detect both supermassive black hole systems and also the same types of systems that LIGO detects, but much earlier in their evolution when they're much farther apart. And so there's a lot of work that we have to do to make sure that our predictions for the gravitational waves are ready for the next generation of experiments, which will be much more sensitive. So this is a picture that people like to show of the entire spectrum of gravitational waves in our universe that we're aware of, Right now, we're detecting things up here at we call it high frequencies, even though it's just 100 hertz. This is what LIGO sees nowadays. You may remember the nanograv and international pulsar timing arrays a few years ago said that they've detected stochastic gravitational waves from all of the supermassive black holes in the universe. That's down here at the nanohertz frequencies. And the LISA mission that's slated to launch in 2034 or 5 will fill in this intermediate range down here, 10 to the minus 3 hertz. And on the vertical axis is how sensitive they are in this thing that's power spectral density per root hertz. Okay, now the main thing that LIGO detects and that the future instruments will detect are gravitational waves from two black holes that are in orbit around each other and eventually merge. This is a cartoon from before the merger problem was actually solved. So analytical methods work for early times, for what's called the in-spiral. Analytical methods work for after the merger, that's called ring down. And in between, for the late in-spiral and merger, there's no analytical method that you can use, so we rely on supercomputer simulations. At the time that Kip Thorne made this cartoon, they did not yet work. That was before 2005. Now we know that it's actually not so scary, but Kip tried to scare people. Okay, so we had the first gravitational wave detection in 2015. And since then, we've had hundreds. And these are all chirps. This is the same kind of broad phenomenology. It starts at low frequencies, and as this binary circles around, emits gravitational waves. It gets closer together, and that makes higher frequency gravitational waves, and they get louder in amplitude, so you get the characteristic chirp sound. Okay. So we have to do things with those gravitational waves, and we need templates to be able to detect them. So that's why we have to make waveforms from theory and from numerical simulations. So where do waveforms come from? This is categorizing all of the types of binaries in this simple parameter space of the mass ratio between the two objects and the separation between the two objects. So when the mass ratio is very large, we can treat the big black hole as the background space, as dominating the space-time. So you can do perturbation theory in terms of the small mass ratio. And when they're widely separated, you can use v squared over c squared or gm over the separation r as a small parameter that you can do an expansion with. And this is called the post-Newtonian theory. And so here, you get things that look like Newtonian gravity plus corrections. And so this is where analytical methods work. And then down here, where we have comparable mass ratios and or going towards the two black holes merging, that's where we need numerics because nothing analytical works there. So at the end of the day, some of us theorists' job is to produce waveforms. That's that red H. That's what we want, and we usually write it in terms of a decomposition in something like spherical harmonics. And there are a whole bunch of analytical or semi-analytical methods for producing waveforms. So I already mentioned post-Newtonian theory, the small mass ratio expansion. There's something called effective one-body. Then there are these methods, phenom and also effective one-body, which are not completely, first principles. They also bake in a bunch of assumptions, and at the end of the day, these things have to be calibrated to the ground truth that comes from numerical relativity. So numerical relativity is the ground truth for the waveforms from merging black holes. The bad thing is you can't say, we have an event, let's go and simulate the gravitational waves from that event, because that can take weeks to months to do one simulation. And if you're a data analyst, you want to do Monte Carlos or something similar to get the parameters out. And so that means you want like millions of waveforms. Obviously, we're not going to do millions of numerical relativity simulations for each event. So numerics have a limitation. And so at the end of the day, we do things like surrogates, which are data-driven models that are trained on these numerical relativity waveforms and that are, as far as we can tell, the same accuracy as the numerical relativity data that they're trained on. So that's the kind of big picture of where these waveforms come from. So let me tell you a kind of 5-second summary of how numerical relativity works. People have been trying to do numerical relativity since, the first time people got access to computers and had enough time. So 1964 was the first recorded attempt to do the two-body problem on computers, and it took until 2005 before we could actually do an in-spiral merger ring-down simulation. And so let me show an animation. I don't know why this doesn't work. Okay, I have to leave to start the video. All right, so this is the waveform down here. That's all that LIGO sees, but we're simulating a whole three-dimensional space-time. Both, we chop it up into space and time. And at every point in space-time, there's a full four-dimensional metric. And here's a bunch of components that are visualizing various types of curvatures. And you can see we track these things called apparent horizons in the simulation to know where the black holes are. And there's a bunch of fancy techniques that I'll mention, but I'm not really going to go into any detail about how the numerics work. Okay, so our numerics simulate a whole four-dimensional space-time. And so what are we simulating? We're simulating this set of partial differential equations. With black holes, there's no right-hand side. The stress energy tensor TAB is 0. So this is a nonlinear second-order partial differential equation in 10 variables. But if you want to put it on the computer, you have to do this kind of extremely ugly thing. So don't tell any of your geometer friends that we do this. It's too messy. They'll be sad. So we break up space-time into space and time. And we break down all of the fields, and we have auxiliary fields, and there's damping, and there's gauge choices, and whatever. But at the end of the day, we have a robust code. We have a pseudospectral code. I don't think I have to go into any of these things. If you want to know what any of these things mean, then please ask me afterwards. But the point is that now we have robust codes for doing numerical simulations of two black holes going around each other and merging. This is a picture of one of our sets of domains. It's broken down into a bunch of subdomains. There's super complicated control systems that try to adapt the domains while the simulation is going on to keep the apparent horizons in certain places where we know them. And yeah, so there's decades of experience of figuring out how to make these codes extremely finely tuned to this particular problem. All right. Are there any questions before I talk about our catalog? Yeah. You mentioned before that the numerical relativistic ground truth. Is that an approximation to the theory equation? Why was the numerical? Well, yeah, I mean, that when we do an analytical expansion, there's also an error in our calculation. So when we're doing post-Newtonian theory, post-Newtonian theory is known to not be a convergent series. It's only an asymptotic series. So adding more terms will not necessarily help. Same thing with the small mass ratio limit. It will not necessarily converge. It's not like we've seen that they don't converge, but we know that they're not fundamentally correct. They're just approximations to actually solving the equations. Yeah. This one. Oh, okay, yeah, this one. Oh. Let me think about whether or not I have an intuitive answer for that or not. Yeah. So for pulsar timing, how low this is depends on how long you're willing to wait. So you want to make the sensitivity better, you have to wait longer and longer. So the data set that was used to say we've detected stochastic gravitational waves from supermassive black holes. That was from 15 years of observation. And this goes down with some sort of power law in how long you have been doing those measurements. Yeah, that's like, integration time improves your measurement. Uh, I don't know. I don't have off the top of my head a quick intuitive answer for why it's shaped like this. But, sorry, I'll try to think about it. Yeah, some numerical. I mean, not in the past, but even still today. Yeah, other codes use the puncture method. Yeah, we don't do that because we have excision. We cut out the interior because it's not causally connected. Information can only go, out of the information can only go into the horizon. So whatever is happening inside these regions can't affect the exterior. So we just cut it out completely. Yeah. Mm-hmm. Mm-hmm. Yep. It's locally non-expanding trapped surfaces. Yep. Yeah. So I mean, you don't get to know where the event horizon is until you have solved for the entire space-time. So we can't locally detect the event horizons. Apparent horizons have a local definition. And in vacuum GR, there's a theorem that tells you that the apparent horizon is always interior to the event horizon. So if you cut things out interior to the apparent horizon, you're also cutting things out that are interior to the event horizon. So you're safe in, you're not throwing away anything that can possibly affect the exterior. But this is something that you can locally find in the simulation. You know where the apparent horizon is. You don't know where the event horizon is until if you've saved the whole four-dimensional volume data and you're done with the simulation, you can then go and ray trace backwards in time to figure out where the event horizons are. I don't know the name. I'm sorry, but yeah, we can look it up. I feel like it's probably in Wald. Okay. All right. So now it's time for a word from our sponsor. This colloquium brought to you by the Simulating Extreme Spacetimes collaboration. So all of the results are done with many people. I am at one of these institutions, but there's lots of people collaborating. We have teleconferences all the time. We all work together. All right, so this is basically just advertising for the most recent catalog paper, which is from last year. So this is our third catalog. There was one in 2013, there was one in 2019, and now it's 2025. I am one of these people. And so, why am I advertising this? Because I want people to actually use the results of our simulations. So, there are people who are, building pipelines for LIGO to use that use these results, but you can use them for anything you want. So the most recent results, we have extended coverage of the parameter space of the binary black hole problem. We have almost doubled the number of simulations. We have denser coverage in the parameter space of, the kind of bread and butter type of simulations that we do. But then we're also pushing the boundaries to higher mass ratios, higher spins, higher eccentricities, even scattering problems where we have an unbound binary where they just do a passage and then fly away. And I think the main thing about the most recent catalog is that we're trying to emphasize quality control in the results. So every simulation we do at multiple resolutions. We also have versioning because sometimes we're constantly trying to improve the code. And so that can change results. And sometimes we have to take previous data and reprocess it. So we'll update the version number, things like that. We did a bunch of studies of how well are these numerics converging, because these are numerical. You have a finite number of pieces of data that's truncated, and you have to check that you're actually converging to some continuum solution. And if you ever discover any data issues, you can go to this URL and open an issue so that we can, deprecate some bad data if there's bad data. Now, all of these things are publicly available. There's a nice package. You can install it. It's hopefully sufficiently well documented. If not, open a bug report. And there's also an interactive notebook. So what's in the data that you can access? There's multiple resolutions for each simulation. There are the waveforms themselves. There's a bit of extra data that is written down on the apparent horizon surfaces. And I'll get to more of this later, but all of these waveforms have had some center of mass correction and also a memory correction applied to them. And there's a whole bunch of auxiliary data about like, when did the simulation take place? So you can tell like, is this trustworthy because it was run in 2024, or is it from 2013? So you should probably not trust things from 2014. So here's just a picture of the kind of most extreme types of systems that we've simulated. So in the top panel, there's the waveforms viewed from some particular direction of an observer of a processing binary that we've simulated for a very long time. And as the orbital plane processes, you get to see modulation in the gravitational waves. So when it's edge on, you would see less radiation than if it's face on. So if you're in a particular direction and the orbital plane is wobbling like this, you get to see some cool modulation. And that would carry a ton of information. So that's one of the main reasons that if we get lower frequency detectors, we'll be able to learn a lot more about these systems than if you only see the last 5-10 cycles. In the middle panel is the difference between an eccentric in blue and a quasi-circular in spiral in black. So we tried to kind of line up roughly as well as you can do by eye the frequency at the beginning here. But the eccentric one has more radiation because it comes to a closer pericenter. So there's more radiation at pericenter. So the blue one inspirals more quickly than the gray one. And in the bottom panel, there's a blue is a high mass ratio, and black is a mass ratio of 1. And the time axis for the blue and the black are different. They've been scaled by this symmetric mass ratio nu. So the blue one, the time is ticking about 5 times faster than the black one. But this is basically the radiation reaction time scale. So at high mass ratio, it takes a lot longer to inspiral than at low mass ratio, at comparable mass ratio. And you can also see that the amplitude depends on the mass ratio. Yeah, so we're pushing the boundaries of the parameter space. All right, so here's a corner plot. If you're an astronomer and you like to look at corner plots, here's the catalog. This is the mass ratio, some quantities that measure spin called chi effective, chi1 perp, chi2 perp. So the blue is the 2019 catalog, and here's the orange. So this is expanding the parameter space coverage. Okay. And this is how long our simulations are. So we're spending more time doing the simulations. We're pushing the median simulation length to be longer, which of course is relevant for lower frequency detectors. This is a distribution of the eccentricity measured at some reference time. So you see this pile up at eccentricities below 10 to the minus 3. That's because we've spent most of our time trying to simulate quasi-circular inspirals, because gravitational radiation actually tends to circularize binaries. So what LIGO sees a lot of are quasi-circular by the time they get to merger. Now we're trying to fill out this high eccentricity region more, because at lower frequencies, you expect things haven't had enough time to circularize yet. So that's something that we need to do in the future. All right, so quality control, this is what I think is the main thing about our catalog. So everything has version numbers, that's new. The metadata is also versioned. We have a new mechanism that we can say some simulation has become deprecated, because we found some problem, and the package will also find a most similar simulation in parameter space through some metric if you want to find something similar, but the one that you wanted was deprecated. So here's an example of looking at quality control. We do things at different resolutions, which we call LEVs. So this is the highest resolution for this one, called Lev 3, and second highest, called Lev 2. In black is the squared, well, the L2 norm of the strain integrated over the whole sphere of the waveform. And in red is the L2 norm of the difference between the highest and second highest resolution, again, integrated over the whole 2 sphere. So it starts out being 10 to the minus 3. Then there's a bit more error once you get close to the end. And on the bottom panel is the phase error. So how well are the 2 different resolutions staying in phase with each other? So that's where most of the secularly growing error comes from. You can break this down mode by mode if you know about this mode decomposition. So each one of these modes, there's a different amount of error in each mode. The red is the difference between the 2 resolutions. Scaled, multiplied by 3 so that you can actually see it in some of these. So you can see it by eye. Okay, anyway, usually we quantify this by taking the 2 sets of waveforms, taking the difference between them, and doing the L2 norm over the whole 2 sphere, and then normalizing it by the the power in each of the separate modes. So this is kind of like the cosine between the 2 vectors, roughly. So we have distributions of this waveform difference quantity. Sorry, it's 1 minus the cosine, roughly. So you want this number delta to be small. You can see that roughly you can trust our waveforms to a median of around 10 to the minus 4 in waveform difference, but there's a whole distribution depending on how hard of a binary it is. So if it's processing, then it's hard, harder. And if it's non-processing, it's easier. So processing is probably over here and non-processing is over here. All right, so I'm not going to jump into the details. You can break this down by mode. Let me move on to how do you actually access these things. This is mainly driven by Mike Boyle at Cornell. There's a package you can install in the usual way with Conda or UV or whatever your favorite package manager is. And it will do basically everything for you. So, you can load a pandas data frame and do whatever complicated query you want with the data frame to figure out like what simulations have what eccentricities, and then find the one you want and load it. And if you do sim.h, if that waveform is already cached on disk, then it'll load it from the file. Otherwise, it'll go fetch it from the web and download it for you. And then this is how you make a plot. You just say plot of h.t versus here, just for simplicity, the real part of the 2.2 mode or the real part of the 2.0 mode. So if you take this code and you run it, this is what it gives you. Okay, so literally this amount of code will give you a plot of this particular simulation's waveforms. By the way, this shift in the orange that you see here, that's the memory, which I should talk about soon. All right, so if you want to, you can use this interactive version of the catalog at this website. I don't know if anybody's trying to scan the QR code. Okay, I'll wait a second for people to scan it. But there's a little web page where you can kind of get all of these columns of all of the properties of the metadata, and you can see distributions. Can I zoom in on this? Oh, no. Okay, I can't zoom in. You can see distributions of where these things are in parameter space and use that to like down select which simulations you're interested in. Okay, so of course there's more work to do on the numerical relativity side, pushing the boundaries. And then I'll talk more about this Cauchy characteristic evolution thing later. And then everything that I've talked about so far was generated with this code called spec, which long term we hope to replace with this new code called specter, which you can ask me about later if you're interested. All right, so that was our advertisement portion of the colloquium. I guess there were already some questions, but are there any questions about this message from our sponsor? Yeah. Nothing was necessarily wrong with them, but the code has improved a lot since then. Just accumulation of a large number of small improvements. Okay, so now let's move on to the main event. So a lot of this main event has to do with this thing called gravitational memory. And one of the things that I spend a lot of my time thinking about is hybridization, which is a way to combine numerical waveforms and analytical waveforms to get the power of both. Okay, so overview of the stuff that I want to talk about in the remaining, how long is that? Is it 25 minutes? When did we start? Okay. All right. Let's see how much of this I can talk about. So I'll tell you how we currently get waveforms out of numerical simulations. That's called extrapolation. And another method that is going to replace it called Cauchy characteristic evolution. Then I'll mention something called the BMS group, which is the symmetry group that acts on the waveforms, actually acts on the entire asymptotic portion of the space-time that we're interested in simulating. And then finally, how to connect numerics and analytics. All right, so you don't have to absorb everything from this slide. In fact, maybe I shouldn't have even put this equation on here, but we have a computational domain. This is like a space-time diagram that you would have in like a special relativity class. So we break our space-time up into space and time. Each of these green surfaces is one instant of time in the simulation. And we choose a bunch of vertical slices here. So those are spheres of constant coordinate radius. And on those spheres, every time step, we dump a bunch of data from the simulation on those spheres. Okay, and now in post-processing, we try to find outgoing null surfaces, outgoing light rays that go through all of these spheres, because in general relativity, gravitational waves travel on these null surfaces, same as light. And we know analytically what gravitational waves look like in the asymptotic region on these surfaces. So you do some interpolation, you kind of have an approximation for what the surfaces of constant retarded time are, and then you do a fit. You do a polynomial fit in powers of 1 over r, 1 over a good coordinate r. And the piece that we're interested in is the slowest decaying part. So it's the 1 upon r piece of the strain here. So we try to do these fits and then read off the 1 over r piece of the fit. And that's the waveform that we extrapolate to infinitely far away. Now, this is just an approximation. This is not actually solving Einstein's equations all the way out to r equals infinity. But it's a reasonable approximation. So something that's strange about this is this method ought to capture an effect called the memory effect that I'll go into a little more detail later. So the memory effect is after a gravitational wave passes, there is a permanent distortion to distances in space-time. So you might have had two free-floating particles that started out a meter apart. A gravitational wave passes, and afterwards they are a meter plus 10 to the minus 20 meters apart, or something like that. Okay, so there's a memory of gravitational waves having passed. Now, this extrapolation procedure should in principle be able to capture this effect. However, in practice, for some reason that's not completely clear, maybe it has to do with effectively filtering the low frequency nature of memory, it doesn't capture it. So you can kind of in post-processing go back and add in the memory using a balance law. And for people who know about GR, this is essentially the integrated Bianchi identities at future null infinity. But anyway, there's an analytical way to say, if I hadn't captured the memory, how would I add the memory back in? And there's some equation for that. So we have post-processed all of our extrapolated waveforms to add in this memory that we think they're missing, which this is not some self-consistent thing. This is just an approximation to what we think is more correct. Okay. So all of those waveforms that I told you about that you can download right now, they have this memory correction applied to them. What would be ideal would be instead to actually solve Einstein's equations all the way out to future null infinity. This is a conformal diagram, a Penrose diagram. We've compactified spacetime, and in an asymptotically flat spacetime, the boundary of spacetime that we care about here is future null infinity. So gravitational waves that come from this binary merger go out along these null rays, and we're interested in what you would measure if you're infinitely far away in the distant future. So as r goes to infinity at the same time as t goes to infinity along a null ray. Now, there is a formulation of the Einstein field equations on these outgoing null surfaces. You can have a foliation of spacetime by null surfaces, and as long as there's no caustics or anything out here, you can write down Einstein's field equations on these surfaces, and you can actually compactify these null surfaces and solve Einstein's field equations on those surfaces. So you wouldn't be able to do this with space-like hypersurfaces that go to I0 to space-like infinity, because you would have an infinite number of oscillations of gravitational waves on those space-like hypersurfaces, and you would have an essential singularity, and there's no way you could ever resolve it. But on an outgoing null surface, there's only a finite number of oscillations, so you can resolve it, and you can compactify it. So there's some, okay, this slide is just a scary slide. I don't even know why I included it. But anyway, there's a formulation of the full nonlinear Einstein field equations that have a pretty nice form. And we've implemented this in Spectre. So we have a code that will solve Einstein's field equations on these null surfaces. So if you take data on that wiggly, what we call world tube here, if you take boundary data on that world tube and one initial data surface on one of these hypersurfaces, then you can evolve the data for the external region of the spacetime all the way out to future null infinity. Okay? And so we now do this, although we haven't published a catalog with it yet. We've made 13 simulations available using this method, but we're doing a bunch internally. We're still trying to work out some kinks, but anyway, we can now solve Einstein field equations all the way out to future null infinity. And this means that we can resolve the memory correctly instead of having to do this post-processing memory correction thing. At the same time, we don't just get the strain, we get all of these other quantities called Weyl scalars, which you can ask some of your colleagues here what Weyl scalars are if you don't have them at the back of your mind already. Okay, so I mentioned this already. This is the memory effect, that after a gravitational wave passes, there's a permanent distortion to the separation between objects that were at some initial separation. So before we had this Cauchy characteristic evolution code, almost all of the gravitational waves that you would see in people's talks looked like this, where after the gravitational wave passed, the strain went back down to 0. And those were all wrong. So it's true that the curvature goes to 0 after the gravitational wave passes, but the strain does not need to go to 0. So the one way of thinking about this is, in some fancier language, this is a vacuum to vacuum transition, but we're going from one set of Minkowski coordinates to a different set of Minkowski coordinates. Okay. And there's a gauge invariant way of saying that the difference between infinitely future times and infinitely past times, that's actually gauge invariant. The main place where the memory shows up in gravitational waves is in the 2-0 mode. Well, when you orient your coordinate system in a certain way. All right, now, all right, what does this have to do with something called the BMS group? So we're treating these gravitational waves as landing on this surface called future null infinity. And future null infinity is, every point on here is a 2-sphere. So we've got a 2-sphere crossed with the real line. And we have freedom on, this is the fundamental thing about general relativity. You should have coordinate freedom, right? So there's an infinite number of ways to reslice future null infinity. Now, that's actually too much freedom. You can fix as much freedom as possible. There's a universal structure on future null infinity And so you can kind of make some choices and say how much symmetry is left. So I don't want the whole diffeomorphism group. I want to be able to fix as much as possible, but not fix away the physical degrees of freedom. So what's left over is called the BMS group. The BMS group is the symmetry group of future null infinity and also past null infinity. But it includes the ability to reslice future null infinity. Now, this is itself a null surface, and on a null surface, there's a whole bunch of null generators. And if you think of those as asymptotic observers, those observers cannot communicate with each other. Light cannot make it from one generator to another generator because they are already moving at the speed of light. And that's why they cannot synchronize their clocks with each other. So the freedom that you have left over is the freedom to advance and delay the watch of every one of those independent observers around that whole two-sphere. That's the reslicing freedom on future null infinity, and that's the action of the BMS group is doing that reslicing. Okay, so you can interpret it as a direction-dependent space-time translation or direction-dependent time translation, if you want. And you call those super translations. There's a subgroup of this that is super translations, and it's a semi-direct product with the Lorentz group. All right, now LIGO is, okay, first of all, we're not in an asymptotically flat space-time, but whatever. We're going to pretend that we are. And the LIGO detector would be one ray that's not infinitely far away, but still we're pretending. One ray that's very far away. So it doesn't care about this infinite reslicing freedom. Nonetheless, because we model the entire space-time and we model all of the modes, and a mode is non-local, right? It has some angular structure, the spherical harmonic structure. When we perform gravitational wave modeling, we have to care about the entire family of observers, not just one particular observer. So when we do waveform modeling, we do care about this freedom, even though LIGO at one particular ray would not care about that freedom. All right, let me just give you some visualizations of what this reslicing freedom looks like. So if you perform a Lorentz boost on Minkowski space. So I have a green line, which in the first frame of this movie was just the coordinate 0, 0, 0 in Minkowski space. Oh no, sorry, this is a translation, not a boost. If you perform a translation of the coordinates, then you can see that this line is getting closer to the right-hand side of my Minkowski diamond, which means that its outgoing null rays will land on the right side of this Minkowski diamond earlier than on the left-hand side, right? So what you would write down for a description of the gravitational waves at future null infinity, if you sliced future null infinity with horizontal slices, that description changes when you shove the interior of the spacetime over by 5 meters. And it changes by the light arriving earlier on the right and later on the left. And if you do a boost, so now this is a boost in I guess the x direction, going to the right, or maybe in the negative x direction. So this, I know this probably looks totally unintuitive, but this is actually the action of a boost on that same trajectory. So here you should be able to see that there's some, so these null cones that are landing on future null infinity are ticking away at intervals of constant proper time along that world line. So you're getting a Doppler boosting on one side and a Doppler deboosting on the other side. So the temporal signature is changing. You're changing frequencies by doing this boosting. All right, so that's also in the BMS group. And another way to visualize the action of the BMS group is with these cylinders. So let me just skip to the super translation one. Oh, is this an animation? That's not an animation. Okay, so if you make it a cylinder, So the vertical, oh, my laser pointer died. All right, the vertical direction is going forward in time, and the around direction is one of the angles. So we started out with some, this cylinder would have started out with horizontal slices. This is the action of a translation. This is the action of a boost, where you see you get Doppler boosting on one side and deboosting on the other side. And this is the action of a supertranslation, which is just deforming what you call a surface of constant time, but the same deformation at all times. That's the amount of freedom that you have. Okay, so for the experts, I don't think I need to go through this. BMS acts on the coordinates on future null infinity in some particular way, and that induces an action on the waveforms of a certain type. And we like to work with modes. So if you take this action and you break it down into different modes, then you'll have here I expanded it. You'll have a product of one angular function with another angular function, or really an arbitrary number of them. So that will do some mode mixing. And there's also some offset. Okay, so this is something that was not really appreciated until a few years ago. That the waveforms that you get out of numerical relativity, they are in some frame. They have come with some gauge choice, and you have to know what that gauge choice is to be able to know whether or not these waveforms agree with something analytical or something like that. So okay, so you might ask yourself, is there some canonical frame choice? The answer is no. There's no canonical frame choice for the BMS group. As close to canonical as you can get is you can say, if you go to arbitrarily early or arbitrarily late times, then you're kind of asymptoting to a stationary spacetime. And in a stationary spacetime, there is a canonical choice up to some rotation. You can make this particular thing called the mass aspect be spherically symmetric, and you can make this angular momentum aspect be just a pure L equals 1 function. So this tells you about being centered on the source of the mass in the spacetime and having the angular momentum aligned in a certain direction, and that the strain goes to 0 at either arbitrarily early or arbitrarily late times. So this you can think of as a generalization of being in a center of mass and center of momentum frame, but generalized to the whole BMS group. So that's about as canonical as you can get. And whenever you talk about some analytical calculation like post-Newtonian theory or black hole perturbation theory, it's in some particular frame, but people were not making explicit what frame were they in. So if you want to compare numerical relativity waveforms with those analytical waveforms, you have to go and figure out what assumptions did they actually make. Okay, so let me show you a small example of being careful about your frame choice. So this is the 2-1 mode in blue, coming out of some simulation. And it's an equal mass non-spinning simulation. So if you know something about post-Newtonian theory, then you know something about the frequency of the 2-1 mode as compared with the frequency of the 2-2 mode. Maybe it wasn't equal mass. Okay, to be determined later. Now, in this inset, I'm showing the 2-2 mode. So what you should be able to see here is that the frequency of the 2-1 mode and the 2-2 mode are the same, which is wrong if you've done any post-Newtonian calculations. You should find that the M mode has frequency comes with the waveform evolution going as e to the I m phi. So we should find that the 2-2 mode has twice the frequency of the 2-1 mode. And why are we getting the same frequency in the 2-1 mode? Because it's been contaminated by the 2-2 mode by mode mixing. So if you do a center of mass correction, but just using your Newtonian idea of center of mass, then you notice in the legend here that I've knocked off 2 orders of magnitude of the error of this mode mixing. So I fixed the problem by a factor of 100, but it's still the same frequency. Now, if you use the entire BMS group to fix, to find the correct frame, then you knock off the remaining order of magnitude, and you're left with a waveform that's at half the frequency of the one that we started with. So we've undone the mode mixing by going to the correct frame, right? So you need to know your analytical stuff to know that that frequency was wrong and it was being contaminated. And you need to understand the BMS group and figure out how to go to the correct BMS frame to fix this. Okay, I don't think I need to go into the details of how we do the frame fixing. One of my grad students right now is working on improving the current COM frame fixing. But let me, all right, so I didn't even get to this, right? I guess I'm gonna blaze through the rest of this in the 0 remaining time. But let me talk about black hole perturbation theory. This is not too hard to understand, I think. So when you take a black hole spacetime and you say, okay, at the very end, when the two black holes merge, I'm left with one remnant black hole, but it's a deformed black hole. I'm going to use the structure of my analytical Kerr metric to try to model that whole spacetime as just a perturbation to the Kerr spacetime. So magically, there's this thing called the Tucholsky equation that lets you do that with just a scalar instead of a set of coupled tensor equations. So that's amazing in its own right. But anyway, what is not written here is the fact that when Tucholsky wrote down the Tucholsky equation, he made some implicit assumptions about the BMS frame that's involved here, right? But nobody was talking about what is the BMS frame of the waves that are coming out of my Tucholsky solver. Okay, now one of the things that you can find from the Tucholsky equation is a bunch of damped harmonic, well, it's like a bunch of damped harmonic oscillators, right? As Sidney Coleman told us, all we know how to do is damped harmonic oscillators, or harmonic oscillators. Okay, so black holes are also damped harmonic oscillators. There's a whole spectrum of modes here. This is the complex frequency plane. There's this whole family of modes. And analytically, it looks like the solutions at late times are just a linear combination of a bunch of e to the minus I omega t's. And that makes you think, okay, at arbitrarily late times, the strain should go to 0. They're all damped harmonic oscillators. So that's what it would look like, right? And in fact, that's what it does look like. So this is the 2-2 mode, numerical, and a fit to it with where the amplitudes have been fit, but the frequencies are coming from black hole perturbation theory. And by eye, they look just fine, right? Oh, I said this already. It's just a linear combination of a bunch of damped harmonic oscillators. Now, if you say, okay, the strain is going to go to 0 at arbitrarily late times, and you know about the BMS group, that tells me about what frame I'm in. It tells me that I'm in what's called the late time super rest frame, which is not the frame that the numerical relativity simulations waveforms are in, right? So that same plot that I showed you, that's like the top left panel here. But if you actually take the difference and plot the difference, which is in the bottom panel, then there's some error here, 10 to the minus 2 or something like that. Okay, now if you go to the right, there are 2 different ways that you could fix this. What some people have done is they said, okay, this is just off by a constant. That's all the BMS group does. It just shifts the strain by a constant. That's not true. It's a reasonable approximation, but if you shift things by a constant, then you get this red curve. Whereas if you do it the right way, then you get the black curve down here. So the red curve has not undone the mode mixing. It has taken care of that shift, but it hasn't undone the mode mixing. So you can get your error down to the 10 to the minus 5, 10 to the minus 6 level instead of the 10 to the minus 3 level if you're trying to do precision things. This problem is glaringly obvious if you look at the 2-0 mode, which is the dominant memory mode, right? So in the frame that just comes out of our simulations, this is what the 2-0 mode looks like. This is the blue curve, right? Try as they might, a linear combination of damped harmonic oscillators is never going to settle down to this constant value of 0.1. So obviously the error is order 1 here. But if you transform to the correct late time super-rest frame, then you undo all of the mode mixing and you get your error down to the 10 to the minus 4, 10 to the minus 5 level. Okay, so if you want to compare numerics with this analytical thing that's coming out of perturbation theory, then you got to make sure that you understand what is the frame that those results were in, both the analytics and the numerics. All right. Let me mention something that was enabled by all of this stuff where we're trying to do like, push the precision. Now, general relativity is of course nonlinear. So if you had asked anybody, is there such a thing as nonlinear ring down? They should have told you, yeah, obviously there should be nonlinear ring down. But everybody had just been modeling their ring down by just taking numerical relativity simulations and fitting them with linear perturbation theory. Nobody had, well, that's not completely true. Lionel London had tried in 2014, I think. But the quality of the simulations were not that good, and there was no discussion of BMS frames or anything like that. So now we did some precision stuff. We made sure that we were in the correct BMS frame, and we fit the 4-4 mode. The 4-4 mode because this is the place where the nonlinearity shows up the strongest, because the 2-2 mode is the loudest mode, and the 2-2 mode beats against itself to generate a 4-4 nonlinear mode. So the top curve here, the black curve is the numerical relativity curve, and there's also the model, the blue dashed curve that's on top of it. They're kind of indistinguishable except over here on the far right-hand side. This model that I'm fitting to it is a combination of linear modes plus one quadratic nonlinearity. And the quadratic nonlinear mode is the green dashed curve down here. Now, what you should notice about this green dashed curve is that it is longer lived than the second most important linear mode, which is in yellow, right? So you might think, if I'm doing linear perturbation theory and modeling the 4-4 mode, I'll get the fundamental and then the first harmonic, first overtone, and so on and so forth. But actually it goes fundamental is the most important, and then quadratic nonlinearity is second most important. And then it goes back to being this first overtone of the linear model. That's next most important. So in principle, you've got to get the quadratic nonlinearities right if you want to model the 4-4 mode. Okay, so nonlinear modes can be more important than linear modes. So again, not really a surprise because everybody knows that GR is nonlinear, but you have to look very carefully to compare the fully nonlinear numerical relativity simulations with the analytical approximations. All right, I don't think I'll even mention tails because I think I'm out of time. And I guess I won't even talk about surrogates or hybridization. Okay, so if you want to know about surrogates or hybridization, then I guess you have to read one of these papers or come talk to me. But the like 1 second summary of this is, if you want to extend your waveforms to arbitrarily early times, then as you go farther and farther back in time, that's when the analytical methods of post-Newtonian theory get better and better. So what you should do is you should stitch your numerical relativity waveforms with your analytical waveforms. But again, if you want to get the stitching right, you have to know what frames they're in, and you have to match the numerical relativity frame to the post-Newtonian frame. And that's a big computational problem because there's an infinite number of degrees of freedom of that BMS freedom, which we truncate down to, we have to fit some 90 parameters all at the same time to get the frame right. But okay. Okay, so anyway, because I don't want to steal any more of your time, what should you remember? Well, there's an old way of getting waveforms out of numerical relativity simulations, and that one was just an approximation. There's a new way called Cauchy characteristic evolution that actually lets us solve the nonlinear Einstein field equations all the way out to future null infinity, to the boundary of spacetime. And the data at future null infinity is acted upon by the symmetry group called the BMS group. And you need to know what frame you're in if you want to compare your waveforms that are coming from numerics with analytics. And because we have this tool now, and our numerical simulations are sufficiently precise, we can actually see all of these subtle effects. We can see nonlinear ring down, we can see tails, we can see that our frame, when we're trying to stitch with post-Newtonian waveforms, is not the post-Newtonian frame, and we can solve the big numerical problem of transforming our numerical relativity waveforms into the post-Newtonian frame to be able to stitch them together so that we can have waveforms that are valid to very early times. All right, so there's still a lot of work to be done. We don't have this working for eccentric and precessing waveforms yet. So there's still a lot of work to do. But like once those future detectors are online and we're getting these very complex morphologies that include precession, include eccentricity, I think we're going to see a lot of really cool thing in gravitational waves. So thanks for your attention.